Have you ever wondered what causes the strange and unusual behaviors of some popular materials that can occur in everyday life, which you can't explain why it happens? Like why paint does not set down on the floor, and why is the tomato ketchup so hard to flow out from the bottle when you pour it, and when you stir the yogurt it becomes thinner, but when you just leave it there it becomes thick again.
These phenomena we encounter can be explained by rheology. What is rheology? Want to know? Continue watching then. Rheology, the science of deformation and flow of matter under the effect of applied force. Deformation is a change of the shape and size of a body due to applied force. Flow is an irreversible kind of deformation. The nature of the deformation depends on the body's material conditions. Rheology properties of materials are dependent on time and temperature. So, why study rheology? Rheology is related to how we perceive food because mouthfeel, chewiness, and body are all related to how materials are deformed and flow. Rheology properties of food materials determine how they are processed. Stress is defined as the force divided by the area over which this force is acting. Shear stress, where forces are applied in opposite directions and parallel to the side of the body. It is one of the parameters studied in rheology since it is the stress that a fluid requires to start flowing. Shear rate. Shear rate is the speed of a fluid inside the parallel plates generated when shear stress is applied. Viscosity is a measure of a fluid's resistance to flow. Low viscosity equals to fast moving and high viscosity equals to slow moving. True viscosity is where viscosity remains constant over all stress conditions, mainly for Newtonian fluid. It is a fundamental rheological property describing the flow behavior of the material. Apparent viscosity, however, is where viscosity is dependent on shear rate, so the shear rate must be specified for viscosity obtained, mainly for non-Newtonian fluid. It cannot be used as a rheological property. Now, let's come to Newtonian and non-Newtonian fluid. This graph shows the relationship between shear rate and shear stress for both Newtonian and non-Newtonian fluid. For Newtonian fluid, shear stress is linearly correlated to the strain rate. Non-Newtonian fluid display either a non-linear relationship between shear stress and shear rate, have a yield stress, or viscosity that is dependent on time. For dilatant, the shear thickening fluid, its shear stress accelerates with increasing shear rate. For pseudoplastic, the shear thinning fluid, its shear stress decelerates with increasing shear rate. Bingham plastic requires yield stress to start flowing and then exhibit Newtonian behavior. Herschel-Buckley requires yield stress to start flowing and then exhibit non-Newtonian behavior. This graph shows the relationship between shear rate and viscosity for both Newtonian and non-Newtonian fluid. Newtonian fluid has a constant viscosity even at an increasing shear rate. For pseudoplastic with shear thinning property, its apparent viscosity decreases with applied shear force. Dilatant fluid with shear thickening behavior, its apparent viscosity increases with applied shear force. Newtonian fluid experiences shear stress that is linearly correlated to the strain rate. At a constant temperature, viscosity remains constant regardless of the amount of shear applied. This is true viscosity. Fluid viscosity is only dependent on temperature, pressure, and chemical composition. Examples of Newtonian fluid includes water, alcohol, and oil. How does temperature affect the viscosity of Newtonian fluid? When temperature decreases, viscosity increases. When temperature increases, viscosity decreases. For example, when syrup is cold, it has a high viscosity and can be difficult to pour. When heated in microwave, the viscosity decreases and the syrup flows more freely. Non-Newtonian fluid is where fluid viscosity is dependent on shear rate. The viscosity of fluid changes when stress is applied. The apparent viscosity changes with the rate of shear strain. Examples of non-Newtonian fluid includes paint, ketchup, and toothpaste. Non-Newtonian flow behaviors are categorized to non-time dependent and time dependent. Non-time dependent includes pseudoplastic, dilatant, plastic, and viscoelastic. For time dependent, we have thiotropic and rheopactic.
Dilatant have shear thickening behavior. The viscosity increases as shear rate increases. The examples are quicksand and oobleck. Pseudoplastic, the opposite of dilatant fluid, have shear thinning behavior. The viscosity decreases as shear rate increases. The examples have paint or blood. Plastic flow behavior will not begin to flow until a minimum shear stress, yield stress, is exceeded. Bingham plastic, a non-Newtonian fluid that requires yield stress and behaves like Newtonian fluid once they start flowing. For examples, clay suspension or drilling marks. Herschel-Berkeley, a non-Newtonian fluid that requires yield stress and behaves like non-Newtonian fluid once they start flowing. Herschel-Berkeley fluids include both shear thinning and shear thickening materials. Viscoelastic effect. Internal structure of the material can sustain stress for some time, so when stress is removed, the fluid will remain deformed for some time. This time is known as the relaxation time. Due to the internal stress, the fluid will not instantly return to original form after external stresses are removed.
Thiotropic is similar to pseudoplastic, where viscosity decreases as shear rate increases. The decrease in viscosity is time dependent. Viscosity decreases over time at a constant shear rate because the intermolecular interactions have decreased within the molecular structure with time. True thiotronicity is where original structure and initial viscosity are restored when shear rate stops. Apparent thiotronicity is where original structure and initial viscosity are not restored when shear rate stops because of irreversible structure breakdown. Examples include wastewater and glue. Rheopactic is similar to dilatant, where viscosity increases as shear rate increases. However, the viscosity increase is time dependent. Viscosity increases over time at a constant shear rate because the intermolecular interactions of rheopactic materials cause friction to increase within the molecular structure with time. True rheopacticity is where original structure and initial viscosity are restored when shear rate stops. However, apparent rheopacticity is where original structure and initial viscosity are not restored when shear rate stops because of irreversible structural damage. Examples include gypsum gum and printer inks. This name came from a book written by Dr. Seuss named Bartolomeo and the Oobleck. In the book, there is a king who gets bored with normal everyday weather. Therefore, he makes sticky stuff fall from the sky named Oobleck, which is the stuff we are going to talk about today.
Shear thickening. Mixing equal part of cornstarch and water give you oobleck. The viscosity of oobleck will increase when force is applied. Therefore, it firms up like a solid when being tapped, stirred, or squeezed. Oobleck is a suspension of cornstarch in water. A suspension is a mixture of solid and liquid. In this video here, cornstarch is a solid and water is a liquid. Cornstarch is a large blocky molecule, which is represented in rectangles. The water, which is a much smaller molecule, is represented in circles. When a weak force is applied on the cornstarch by lightly pressing it with a hand, the cornstarch molecules are able to slide past each other due to the water between them that acts like little balls, causing them to roll around. However, when applied with a strong force, the water molecules are being pushed out from in between the cornstarch molecules. This creates an area that's almost entirely cornstarch for the suspension to behave as a non-Newtonian fluid. First, pour the cornstarch into the bowl and then slowly add the water. Stir the mixture until it has a honey-like look. Lastly, you can add colorant, but this is optional. This is how oobleck should behave. When you heat it with strong force, it is hard like a solid. However, when you slowly immerse your hand into oobleck, it will release the pressure and so you can immerse your hand into it, and that oobleck behaves like a liquid. Grab some oobleck in your hand and squeeze it. It becomes a solid ball in your palm. But when you unclench your fist, it will slide between your fingers just like a liquid. Oxidation. One type of modified cornstarch is called oxidized cornstarch. The cornstarch was modified using oxidizing agents such as chlorine, hydrogen peroxide, potassium permanganate, or sodium hypochlorite. Acid modification. The second type of modified cornstarch is called acid-modified cornstarch. This starch is mixed with water, heated and treated with a mild acid. Once the starch properties reach the desired state, the acid was being neutralized using sodium carbonate. The starch is then filtered, washed, and dried. Modified cornstarch can be found easily. It is an ingredient in a lot of products. Modified cornstarch can be used as stabilizer, thickening agent, and emulsifier. Oobleck can act as a protective packaging material because of their non-Newtonian fluid properties. The first is the egg packaging. When the eggs hit the ground, a quick direct force is applied to the oobleck packaging, causing the cornstarch to clump together and harden like a solid. This process absorbs the impact, thereby protecting the egg. The second one is the athletic support. Shear thickening fluid can be used to make mouth guards and gloves to protect athletes from jarring impact, used in sports shoe designs for energy dissipative construction too. The third one is the body armor. Utilize a solution of polymer particles that soak into a porous fiber which are flexible. This material can be used as body armor because it is flexible but hardens when there is an impact from a bullet. Modifying shear thickening fluids so they can flow smoothly is a challenge in many industrial processes. There are two theories about the mechanism for thickening. One proposed theory is that the friction between the solid particles blocks them into configurations that resist flow. The other is that when the particles are being pushed closer, the resistance from draining the liquid between them slows down and locks the particles into clusters. Stress causes particle collisions and drives the thickening behavior. However, according to hydrodynamic model, once the stress surpasses a threshold, particles are unable to squeeze by each other because they are locked into place. This is a problem as fluid will not be able to flow properly.
Here comes to the end of our lesson. Thanks for watching our video. See you next time!